One type of reaction that we need to address explicitly are acid-base reactions. So for acids and bases, we are going to, just for now, look at the Arrhenius definition for these two types of molecules. And we have to look at these because you will see them doing reactions wherein we can apply what we now know about non-ionic reactions, but it won't have seemed like you had an ionic compound to work with to begin with. So let's just do the definitions and then look at how they react with each other. So an acid, according to the Arrhenius definition, is something that produces aqueous H+ in solution. Now, you won't always see this written as H+ because you're not going to find H+ just hanging out by itself, but note that it is listed as aqueous. What this really means is that it is H3O+ in solution. So the H+ is actually attached to a water molecule, but depending on how the reaction is written, sometimes it's just written as H+, but it's important that you know it's not just there by itself. So an example of an acid that we can look at a reaction for is something like nitric acid. So this HNO3 aqueous, and if it produces H+ or produces H3O+ in solution, what this means is that this, as a soluble thing, will produce H+ aqueous and nitrate, so the NO3- aqueous. Alright, so this is how we get the H+ for the acid. We will talk about different types of acids, why this one has a regular arrow, why you're seeing some examples that have different looking arrows that are actually called equilibrium arrows in a later module. Alright, so a base is something that produces OH- in solution. Now these you probably would have written appropriately on your own because the bases that follow the Arrhenius definition are all things like sodium hydroxide. So if we have aqueous sodium hydroxide, this will be a sodium 1+ cation and the hydroxide anion in solution. Okay. Now, if you mix an acid and a base with each other, the reaction that happens is something called a neutralization reaction. And the basic outline for this is that an acid reacting with a base produces a salt and some water. And we will get this just by doing the swapping partners that we did with our ionic equations and net ionic equations in the last video. So if we had something like hydrochloric acid reacting with magnesium hydroxide, if we split these up and swap the partners, right, let's do just kind of some colors underneath. The Cl- is going to pair up with magnesium. The H is going to pair up with the OH. That's how we end up with water as a product. It's from one of the partner swaps. So magnesium chloride, but I need 2 Cl's. And if I go look this up in the solubility table, it is soluble. And then we're going to make a liquid water. Now, I need to make sure that this is balanced. So in order for this to be balanced, I need a 2 in front of my HCl and a 2 in front of my H2O. Okay, now once we learn more about reaction stoichiometry, you'll be able to do more with these. But just like we did in the last video, you can take this molecular equation, you could turn it into an ionic equation, a full one, and then into a net ionic equation. And so this is something that you should practice with. And I will give you the answers so that you can check how to get here. The net ionic equation is going to be that H plus aqueous reacts with OH minus to make liquid water. A second special type that we need to address are gas evolution reactions. And this is just because every time you do a reaction where you swap partners, you don't always get a precipitate like the last video, or a soluble ionic compound. We have a few special cases that we're going to address right here. And this is the case where your product ends up being a gas. And so some gases form directly. And an example of this is H2S gas. So if we did something like mix H2SO4 aqueous with Li2S aqueous, these are both soluble compounds, so we write the ions, we swap partners, and for products we make H2S, which is a gas, and Li2SO4, which is aqueous. And the reason that we know that we formed H2S gas, well, one, this is pretty stinky, so if you made this in lab, you would be able to tell, but also you see bubbles. So the gas bubbles up out of the reaction because that's the form that this product is in at room temperature under the conditions that we're doing this reaction. Other gases come from intermediates. So if you create one of these intermediates when you're swapping partners, you need to turn it into the final product for your final answer. And you will see these in the practice problems or on the problem set for this module. So when you swap partners, I'm going to give you a table. If you form this intermediate, you need to turn it into the corresponding thing in the right-hand column. So if you form H2CO3, this will turn into liquid water and carbon dioxide gas. If you form H2SO3, will turn into H2O liquid and SO2 gas. Hopefully you're seeing a pattern here. If you make NH4OH, right, ammonium hydroxide, it will turn into liquid water and NH3 gas. All right, these are the only three in addition to H2S that I would like you to know turn into gases, and especially for the intermediates, watch out for these because these are easy to skip over.